Yeah, this is Dr. J. Mohan. I am from PC department of Institute of Aeronautical Engineering. I am going to discuss about the Fourier transform for first session. This is a topic of signals and stochastic process subject. Today presentation outline are derivation of Fourier transform from Fourier series, inverse Fourier transform, difference between the Fourier series and Fourier transform of signal function, that is represented as a sine function, then Fourier transform of unit step function. Those topics we should discuss this session. First, we go for the Fourier transform. First, we need to derive the Fourier transform equation from the Fourier series. If the Fourier series going to respond only the periodic signal, but the Fourier transform, it's not consist of periodic signal. It's going to possible to do for any kind of signal cases. First, we must take for the signal, one is x of t. That signal is represented as a non-periodic signal. This non-periodic signal we need to convert for the periodic case. So that's why what we are doing, we make for the some period as a fundamental period condition, that is called for the capital letter T, and let the signal of Fourier case I should write for the x of t, and I take for the Fourier series, that will be represented as a g of t. Now the x of t is represented as a non-periodic signal. Then we write for the relation between the x of t as well as of g of t. In the case of Fourier series, x of capital letter X of t is equal to t tends to infinity as a limitation of g of t. Now the capital letter T I represent as a fundamental period of the Fourier transform, that is called for the g of t. In this Fourier transform condition, that g of t we consider with the Fourier series condition, that the g of t it is going to produce for the coefficient, that coefficient is called for the Fourier series coefficient. That Fourier series coefficient here we represent by the C of n. The C of n is represented as a Fourier series coefficient. Now we go for the Fourier series. The Fourier series we represent for the g of t. That g of t is equal to summation of n equal to minus into plus into C of n e power j n omega 0 t. This C of n is called for Fourier series coefficient. The Fourier series coefficient is represented as a C of n is equal to 1 by t integration of minus t by 2 plus t by 2. Why? Because of this interval we take, the signal is represented as a periodic. The periodic signal it consists of 0 to t only is going to active. For we take for 0 to t, this 0 to t I split for the minus t by 2 and plus t by 2. If we add both for the signal condition, this is going to produce for the 1 t. So now this 1 t is consists of 0 to t. After this is the case, the signal is represented as a periodic. After this 0 to t, again it is going to happen for the t to 2t. The same character is going to display for the what we are going to get from the 0 to t. Same it will be going to happen. So that's why I represent for the coefficient, that is a Fourier series coefficient, C of n equal to 1 by t integration of minus t by 2 plus t by 2 g of t e power minus j n omega 0 to dt. Now what I am doing, I make to cross multiply for the t to C of t, or we should multiply for the both side of Fourier series coefficient as capital letter T. That condition what will be happen, So this here I am going to multiply with the t, here also multiply with it. These two are getting to cancel. For the right side, left side I write as a t c of n is equal to integration of minus t by 2 plus t by 2 g of t e power j n omega 0 dt. In this term, c of n represent the magnitude of component of frequency. That magnitude of component of frequency I should write for the n of omega 0. Now, n of omega 0 is represented as a frequency coefficient. That value is equal to, I should write for the omega at when t is getting for the infinity condition. So we know the omega 0, when we studied for the Fourier series, the omega 0 is represented as a 2 pi by t we write. Now, in this condition, we go for the Fourier transform to convert for the Fourier series to Fourier transform. Due to that condition, what we are doing, we taken for the frequency component of n omega 0 as omega, that will be going to active only t is equal to infinity condition. Now, this condition we make to do for the omega 0 is equal to 2 pi by t, then t tends to infinity. This value is represented as a 0. Okay. So the discrete Fourier spectrum become continuous, and hence the summation become the integral. So g of t is tends to x of t, therefore t tends to infinity. Now, as per the statement of condition, the omega is represented as a 2 pi by t when t tends to infinity. That condition is produced by the 0. So based on that one, we go for the Fourier series coefficient, that is t c of n is equal to t tends to infinity integration of minus t to t by 2 to plus t by 2 g of t e power minus j omega t dt. Now, this case, this limit, it will be go for only g of t condition. So that's why what I'm doing, I interchange for the limit t tends to infinity as integration of minus infinity plus infinity in the left right side of the equation, limit t tends to infinity g of t e power j omega t dt I write. Now, this value I represent as a x of t, capital letter x of t is equal to limit t tends to infinity g of t. So this portion only we make right. So from the equation, t c of n is equal to integration of minus into plus into x of t e power j omega t dt. This whole value I call for the capital letter x of omega. So therefore, the Fourier transform of the non-periodic signal is x of omega is equal to integration of minus into plus into x of t e power j omega t dt. The function x of omega I represent as a frequency spectrum of x of t and is called spectral density. So this equation we call for the Fourier transform of non-periodic signal. This Fourier transform of non-periodic signal, it came from the Fourier series condition. But Fourier series we taken for the only periodic. So based on that case, we make to change for the Fourier transform as the non-periodic into periodic condition. X of omega is equal to integration of minus infinity plus infinity x of t e power j omega t dt. So this major role it will be going to display for only the omega condition. So that's why this signal I call for the spectral frequency spectrum of function or spectral density function. Next, we go for the inverse Fourier transform. So inverse Fourier transform, we go based on the Fourier series only. The Fourier series of periodic signal I should write as a g of t is defined as g of t is equal to summation of n equal to minus infinity plus infinity c of n e power j n omega 0 t. Now we know c of n equal to t c of n. Okay. So as per the previous case, what we studied for here, the c of n, this notation, that is t c of n, I should write as a c of n is equal to t by t c of n divided by t, that value equal to x of omega by t. this T C of n we derived from the equation of previous condition. That value is equal to x of omega. Okay, so this x of omega is represented as a T C of n. So this value I should substitute here. So what is it? C of n, T C of n divided by, well, this will be T is getting to the answer we got for the C of n. Now I should write for this value as T C of n equal to x of omega as per the Fourier series into Fourier transform condition. Now what will be happen? X of omega divided by capital letter T. Now G of T is equal to summation of n equal to minus infinity plus into this term. The C of n term is represented as x of omega divided by capital letter T e power j n omega 0 t. Now I should write as a n omega 0 this values n omega 0 e power j n omega 0. This portion I should write as a omega. So n omega 0 equal to omega. Then t value is represented as a 2 pi by omega 0. Then g of t I should write summation of n equal to minus into plus into x of omega. The t is present here. This value I should substitute this 2 pi by omega 0. I should substitute here e power j n omega 0. So remaining portion. Now I should write as a summation of n equal to minus into plus into x of omega 2 pi e power j n omega 0 t e pi j n omega 0 t into omega 0. Now, as per the condition, we taken for the frequency spectrum function as capital letter T is equal to infinity. In this case, we go for the omega 0 equal to 2 pi by T and T is equal to infinity, then the value is present for the 0. This case, omega 0 can be represented by d of omega and summation become as an integration. So now we changed this summation, we converted for the integration as well as of omega 0 I write as a d of omega. So x of t, now I should write for the x of t is equal to 1 by 2 pi integration of minus into plus into x of omega e power j omega t d of omega. This x of t is known as inverse Fourier transform. Generally, I should write as a Fourier transform as x of t. You take for the Fourier transform, you got for x of omega. If you take inverse Fourier transform, you get for the x of t. That's why I put for the both the side as Aeronautical. This is the way we are finding for the inverse Fourier transform from the Fourier series. So here we need to remember the omega 0 is represented as a d of omega. Then we write for the C of n equal to T into C of n divided by T. That both the T is getting cancelled. As for the Fourier series, we know the T C of n is equal to x of omega. Then we should substitute for here. Then we know the limit that T tends to infinity condition. That condition T is present for the 2 pi by omega 0. Then we should substitute that those value. What are the value? This T value as well as of this n omega 0. This is n omega 0. Both the values substitute here. What we happen? We got for the n equal to minus into plus into x by omega 2 pi e power n omega t dt. So now finally I write for the this summation. It will be converted for the integral. Then this 2 pi is came out from the 2 divided by 1 divided by 2 pi. X of t is equal to 1 divided by 2 pi integration of minus into plus into x of omega e power j omega t d of omega. Now x of t is known as inverse Fourier transform of x of omega. We should write for the general form as x of t used for the both the direction. Now Fourier transform we get for the x of omega. Now we go for the difference between the Fourier series as well as the Fourier transform. First we go for the definition. The Fourier series, what will be happen? Fourier series is a technique of decomposing a periodic signal into the sum of sine and cosine terms. But the Fourier transform, what will be going to happen? The mathematical operation for converting a signal from time domain into the frequency domain. So what the Fourier series is doing? It's doing for the decompose the periodic signal as a sine as well as a cosine terms. But Fourier transform, it's converting the signal as a time domain into the frequency domain. So next case, type of the signals. The Fourier series can be applied to periodic signal only. Why? Because of it's going to satisfy for the periodic condition. If the signal is not periodic, it's not possible to find for the Fourier series. Otherwise, we need to convert the non-periodic signal into the periodic signal. After that, we can apply for the Fourier series. But a Fourier transform cannot be like that one. You can use for the periodic signal as well as a aperiodic signal also. It's going to satisfy for the conditions in the Fourier transform. Next, uses. The Fourier series is used for harmonic analysis of arbitrary periodic functions. But Fourier transform is used to solve the differential equation. So in the Fourier series, it's not at all possible to have for the time-based condition. But Fourier transform, it's going to depends on the time-based condition only. That means we can differentiate, otherwise we can integrate both the condition is going to satisfy for the Fourier transform. Next, we go for the application. The application of Fourier series include electrical, electronics, and signal processing, quantum mechanism, etc. we can use. Wherever we are going to using for the analog condition, we can adapt it for the Fourier series. But in the Fourier transform is in nuclear, magnetic resonance, and other type of spectroscopy application we are using. Okay, so this one it will be going to using for the high-end cases. When the non-periodic signal is received, those cases we are going to apply for the Fourier transform. This is the difference between the Fourier series and the Fourier transform condition. Next, we go for the Fourier transform of sine of function. So what is the meaning of sine of function? The sine of function I represent as a SGNT and is defined as SGNT equal to 1 for t is greater than 0. If minus 1 for t is less than 0. That means when we go for the signal, this is a signal case. When t is greater than 0, the value is represented as a 1. Okay, this is I take for the x of t. When this is 0, when t, okay, t is represented as a greater than 0, it's represented as a 1. If t is less than 0, it's represented as a minus of 1. Okay, so this is represented as a t. Okay, this is a plus t, is a minus t. It's represented as a amplitude. That amplitude is equal to 1 when t is greater than 0. Amplitude is minus 1 when t is less than 0. That's why simply I write as a sine function as 1 when t is greater than 0, minus 1 t is lesser than of 0. This value I should write as a x of t. So this is x of t as e power minus of a mod of t sine t when a is equal to 0. So if we substitute for the a equal to 0 to here, what will be e power 0 is equal to 1 into mod of t. Then e power 0 is equal to 1. Then we write as a sine of t only. That now in this case x of t is equal to sine of t. This is values represented as a 1. Is multiplied with that and a equal to 0. So that's why simply I write as a sine function as x of t is equal to e power minus a mod of t sine of t when a tends to 0. Next, now we need to apply for the Fourier transform for this sine of function. So now you can take for the sine of function can be obtained as x of t is equal to sine sgn of t when when this condition I take for the limit the a tends to 0 e power of minus of a mod of t sine of t. Well, this case x of t is equal to limit a tends to 0 e power minus at u of t minus of e power at u of minus t I should write. So finally my equation, it's consists of minus t to plus t, that is minus t to plus t. The maximum amplitude is equal to 1, the minimum amplitude is minus of 1. Here also minus 1. This case I write as say x of t. This waveform I should write like this form, because of u of t also is represented as a 1, minus of u of minus t is represented as a minus here, that's why it will be consist of this portion. So this portion, it's consist of this place, then this portion, it's consist of this place. Now a tends to 0, a tends to 0 in the sense e power 0 is called for plus 1 only. Okay, from the definition of Fourier transform, we write for the Fourier transform as x of omega is equal to integration of minus 1 to plus d x of t e power minus j omega t dt. Now this x of t we know that is sine sgn of t. Now I write as our Fourier transform as integration of minus into plus into sine of t e power j omega t dt. This case we know this x of t we found for the limit a tends to 0 e power minus of at u of t minus of e power at u of minus t. That this value we can substitute here. So that value will be going to I passed for here. That means sine of t here I substituted for here. Then after we take it out for the limit a tends to 0. Then remaining is integration of minus into plus into e power at e power minus j omega t u of t dt minus of integration of minus into plus to e power at e power of minus j omega t dt u of minus t, it will be represented. After that, we should simplify for that equation. First, the case u of t is there. See, this u of t is going to active only 0 to t. What is that? Here is 0 up to plus t. So this portion I represent as a u of t. Then this portion I represent as a this portion, all this portion I represent as a u of minus t. So now I adapted for the minus u of minus t as well as of u of t as the interval. What is that? The u of plus t is represented as 0 to infinity e power minus of a plus j omega t dt, then minus of integration of minus infinity to 0, minus infinity to 0 e power minus of a j omega t dt. Now in this case we need to simplify. So for here is minus to 0 is present, that's why just interchange 0 to infinity, the sign here is getting to changed minus. Now we can simplify for taking the integration condition. After that we should substitute for the limits. So this integration is represented as e power minus a plus j omega t divided by minus of a plus j omega t. The limit substitute for the 0 to infinity. Here also e power minus a minus of j omega t divided by minus of a minus of j omega. The limit is 0 to infinity. If we substitute the limit 0 to infinity, the infinity condition is represented as 0. E power 0 is equal to 1. So here is I should write as a limit a tends to 0 e power infinity minus of e power 0 divided by minus of a plus j omega minus e power plus infinity, that is means e power minus of infinity e power of 0 divided by minus of a minus of j omega. So this portion is represented as a 1, then this portion also represented as a 1, then 1 divided by a plus j omega minus of 1 by a minus of j omega. This minus getting to cancel for because of this minus. So this is also getting to cancel because of this minus. Then finally I can simplify for this equation. When a tends to 0 condition, what will be happen? So a values are 0, that means 1 by j omega minus of 1 by minus of j omega. Then this value is equal to this minus and this minus getting to cancel, that's why it will be other plus 2 divided by j omega. So this 2 divided by j omega case is represented as a x of omega of sine of function. So if we take for the sine of function of Fourier transform 2 divided by j omega we got. So based on this 2 divided by j omega, it doesn't find for the exact value of where the signal is going to happen. So that's why we should take for the magnitude and the phase response of Fourier transform of sine of function. The magnitude of sine of function is represented as a mod of x of omega is equal to root of 0 plus 2 divided by omega whole square. Why? Because of the real part is 0, the imaginary part is represented as a 2 divided by omega. Okay, this see, so for this case, for here, there is no real part, 0 plus 2 divided by j omega is there. So imaginary part only is going to available. So that's why the real part is represented as 0, 2 divided by j omega whole square. Then we can simplify 2 divided by omega for all values. For magnitude is represented as 2 divided by omega. Next case, we go for the phase response. The phase response is represented as a tan inverse of imaginary part divided by real part. So if we apply it for the tan inverse of imaginary part divided by real part, we got for the pi by 2. For only lesser than of the omega is always lesser than of 0. This condition I write as a angle of x of omega is equal to pi by 2, omega lesser than 0 minus of pi by 2. For greater than, that is omega greater than 0, that condition it's not going to happen. Now we got for the magnitude response as well as the phase response. Then we need to represent for the graphical representation of sine of function as included with magnitude as well as a spectrum. First, this is a sine of function we got. So that is x of t equal to sine of t. So this case, when 0, that is t greater than 0, the amplitude is equal to 1. Minus 1 when t is less than 0. So here is amplitude is greater than value of t. That's why it is represented as a 1. Then amplitude is minus 1 and t is less than of 0. That portion it will be represented as here. So this is a sine of graphical representation. If we take the magnitude, what will be happen of sine case of Fourier transform condition, we got for the 2 divided by omega. The maximum amplitude is equal to 2 when the frequency is going to increase. For the right side of positive value, automatically is going to decreasing like a curve. In the negative side, the minus omega condition, that side also will be going to have the decreasing the negative curve. So this diagram is representation represent as a magnitude response of Fourier transform of sine signal. Next, phase response. What the phase response is happen? The phase response is represented as pi by 2 for omega less than of 0 minus pi by 2. That case, when the plus omega, that is omega is greater than 0, what will be happen? It's got for the minus of pi by 2. Same minus of pi by 2. So this is represented as a omega greater than 0. If omega less than 0, that means it will be represented as a plus pi by 2. It's represented as a plus pi by 2. This is a way we can represent for the graphical representation of sine of function in Fourier transform, both magnitude as well as of phase response. Next case, we take for the Fourier transform of unit step function. We know the unit step function. The unit step function definition as u of t is equal to 1 for t is greater than 0 or 0 for t is less than 0. So this one I should write like this one. U of t is equal to 1 when t is greater than or equal to 0, 0 for t is less than 0. This is a mathematical representation. I should write like this form. Now we go for the express the unit step function in terms of sine function because of we know the sine function. Based on that one, we should do for the case of Fourier transform in the unit signals. Now I write as a u of t is equal to 1 by 2 plus 1 by 2 sine of t. That value is equal to 1 by 2, 1 plus of sine of function of t. Then x of t is equal to u of t. That value we call for the 1 by 2 1 plus of sin of t. Now we take for the Fourier transform. So we know the Fourier transform of f of u is equal to, I write as a x of omega. Where the x portion is there, we should substitute for the 1 by 2 1 plus of sin of t. So now x of omega is equal to, as a Fourier statement, minus into plus into x of t e power j omega t dt. Now x of t, I should substitute u of t. Then u of t, we know what is that u of t is represented as a 1 by 2 1 plus of sin of t e power minus j omega to dt. So now that condition x of omega is equal to integration of minus into plus into 1 by 2 1 plus of sin of t e power j omega t dt. Now we make to do for the integration. So 1 by 2 is a constant, we take it out. Then here is a 1 is there, then 1 into e power j omega t dt of integration of minus into plus into plus of integration of minus into plus into sin of t e power j omega t dt we write. For the Fourier transform of constant amplitude and the sin function is f of 1 is represented as a 2 pi by del of omega, and f of sin of t is equal to 2 pi j. This is we find, this is also we know. If we take for the Fourier transform of 1, that is equal to 2 pi by del of omega. Now we should add for both. The f of u of t is equal to x of omega is equal to 1 by 2 pi del of omega plus 2 divided by j omega. So these are the case we find for previously. For the Fourier transform of unit step function, f of u of t is equal to pi del of omega plus 1 by j omega. This 2 getting to cancel for both the sides. So remaining portion what they there, we write it. Now u of t Fourier transform is represented as a pi del of omega plus 1 by j of omega. So this will be not possible to identify for the where the signal is getting to dominate. Then we take for the magnitude as well as a phase response of u of t of Fourier transform. Now we take for the Fourier transform of unit step function, the magnitude response is represented as a infinitive. Why? Because of both the case, the real as well as of imaginary parts are there. This del of omega is only the omega equal to 0. So if omega equal to 0, then remaining part it will be represented not happen. So that due to that case, I write as a mod of x of omega equal to infinitive at omega equal to 0 or 0 for at omega equal to minus of omega or omega equal to plus of omega. When the 0 omega is 0, that place only it's represented as a infinitive. The remaining portion it's a 0 at omega equal to minus infinitive as well as a plus infinitive. Now we can write it for the graphical representation of our u of t. The u of t we write in terms of sin of function. That's why the unit step function I write for the amplitude is equal to 1. This amplitude when the t equal to 0, the amplitude equal to 1. That's why the 1 when t is greater than or equal to 0, 0 otherwise. This is u of t. So now this term I write as a 1 by 2, 1 by 2 as the case of 1 plus of, that is sin of t we wrote. So this 1 by 2 is 0.5. That's why 0.5 plus 0.5 sin of t we write. Okay. To take the Fourier transform, the Fourier transform is represent for the signal is amplitude of infinitive. What the amplitude is going to happen? It depends upon the maximum of frequency range. That means the sinum, we know what the sinum is doing. It's doing for the magnitude response is both the side as a increasing as well as a decreasing curve. So there is no effect from the constant. That's why it will be represented as a Fourier transform of frequency spectrum is represented as sinum function case only. Then we should refer from this case of Fourier transform in this section. Signals and system communication, SB Latif and AV Opener we referred. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.